evening, everyone. It is a privilege to introduce you to our center, the Center of Advanced Studies and Innovation Lab, in short, CASI Lab, located in Silchar, Assam. Since beginning its journey in 2018, CASI Lab has been working to develop a conducive research ecosystem in the sciences, primarily focusing on mentoring project-based studies for undergraduate, postgraduate, and research students, as well as organizing a series of in-person and online talks. We are firmly committed to providing a democratic, borderless ecosystem that bridges the gap between institutional experts, independent scholars, and grassroots researchers by facilitating collaborative projects regardless of geographical constraints. As we proceed with today's seminar, I invite you to view our modest efforts through the lens of CASI Lab for the greater good. It is my pleasure to introduce our distinguished speaker for today, Dr. Chandrasekhar Radhakrishnan. Dr. Radhakrishnan is currently serving as an associate professor of practice in the Department of Arts and Science at New York University, Shanghai. He is an accomplished researcher with deep expertise in quantum information science, particularly in areas related to quantum resource theory, quantum correlations, and open quantum systems. His work has significantly contributed to our understanding of how quantum features can be characterized, quantified, and utilized for advancing modern quantum technologies. And also, I'm happy today because Dr. Radhakrishnan is one of my collaborators. We have collaborated in many works. And so today he will be speaking on the topic quantum resource theory, a fundamental framework that plays a crucial role in identifying and quantifying useful resources in quantum systems with wide-ranging applications in quantum computation, communication, and sensing. We are truly honored to have him with us today to share his insights and expertise. Without further delay, I invite Professor Radhakrishnan to begin his talk. Sir, it's all yours. You can start right.
Yes. Thank you, Shovik. And can you see the slides?
Yeah. You enlarge it? Yeah. Okay. Yeah, I can.
Can get. Okay. Thank you, Shovik, for the nice introduction. And I would also like to thank you all for joining for this talk. So today, I will talk about quantum resource theory, a field which I have been working on for the past 10 years. And I have kept it only partly technical, and I'll be happy to answer any questions in the middle of the talk as it happens. And as Shovik said, currently I'm working in the Department of Arts and Science at NYU Shanghai. And so this is NYU Shanghai, like our campus, which is located in one of the central districts in Shanghai. And as an institute, NYU Shanghai has been here for possibly like 12 years, and I worked here for 10 years of that now. And my journey into quantum information started at NYU Shanghai. And today I will talk about quantum resource theory, and the outline of my talk will be as follows. First, I will talk about the basic idea of what is a resource, and looking at entanglement, one of the first resource which was proposed and quantified. Then I will talk about quantum correlations, particularly about quantum discord, bipartite quantum discord, and how bipartite quantum discord was not generalized for a long time, and how we were successful in generalizing it to tripartite and multipartite systems. And recent experimental characterization of this multipartite discord with Professor Kavita's group at Aizer Mohali. Then I will talk about quantum coherence, one of my first, where I introduced measures of coherence and distinguished quantum coherences as local and global coherence. And then I'll talk about the applications of coherence and the experimental verification we did. Finally, I'll talk about the influence of non-inertial motion on quantum resources. It is actually a typo. It should be non-inertial motion, not inertial motion. And I'll summarize at the end. So, quantum resource theory, started off with the discovery of entanglement, though we never actually called it as a resource technically and never actually defined any mathematical framework to study them. Um, at the outset, by the word resource, what we mean is any physical or logical asset required to execute an algorithm, or in other words, we can say required to gain technological advantage. That's how a resource is defined. And in classical physics, the chief resources for computation are time, space, and energy. So now we are currently talking about quantum technologies, which involve quantum computing, communication, and quantum sensing. In all these technologies, we need to have certain properties which are not present in classical system, but present in quantum systems, and can be gainfully applied to get advantage. So in this framework of quantum resource, several quantities have been proposed and studied. The chief among them are entanglement, which is the first one to come, and which was followed by discord, dissonance, coherence, purity, superposition, non-Markovianity, steering, and many more. Contextuality, imaginarity. There are several such quantities have been defined. Here, when we talk about correlations, initially in the 90s, there are only three types of correlations were known. One was non-locality, the next one was steering, and the third one is entanglement. These three correlations exhibit a hierarchical relationship with each other. What I mean by hierarchical relationship is, if I have a pure state and let's say the pure state has non-locality, I take a maximally mixed state and mix with it, then the non-locality will fall, and we will have only certain correlations, which we call as steering. And as we increase the mixing, we will get to a point where both non-locality and steering will not be present, but the state will still have entanglement. We can keep on doing this until we lose entanglement. But the idea is, when we have correlations, non-locality is a stronger form of correlations, followed by steering, which is followed by entanglement. So entanglement was actually more uh, studied in a more detailed way. The first set of papers defined entanglement, and they gave some measures for entanglement like concurrence, von Neumann measure, negativity, and so on. But in the paper by Vedral, he proposed certain criteria for entanglement measure, which is like entanglement should be zero if and only if sigma is a separable state. That is, any state which is separable should not have entanglement. Then local unitary operations should not change the amount of entanglement in the system. And finally, entanglement cannot increase under local general measurements and classical communication, which currently we call this set of measurements as LOCC, local operations and classical communication. Based on these three criteria, several measures were proposed, but the chief measures were negativity, von Neumann entropy, and concurrence. Von Neumann entropy actually defines entanglement as the entropy of the partial density matrix, and it can be defined only for a pure state. The next quantity is negativity. In negativity, we employ this idea that if we have a map, like a partial trace map, which is not completely positive and trace preserving, it is positive and trace preserving, but not completely positive and trace preserving. So the deviation between this positive and trace preserving and completely positive and not trace preserving, this deviation captures the entanglement. That's negativity. And then we have concurrence. All these three measures work only for systems with 2 qubits, or possibly like a negativity works for a system which has a qubit and a qubit. Mm, Then But to measure entanglement in multipartite systems, we need to define uh, measures which are based on distance measures. A distance measure is one in which we consider the density matrix in the Hilbert space and find the distance to the closest separable state. Now, this distance, we can use any distance to find it, and this distance can be like L1 norm or L1 norm or relative entropy or any of them. But this distance measure should satisfy certain properties. Some of the important properties are, if I have two density matrices, X and Y, the distance between them should always be greater than 0, as long as X is not equal to Y. And if I take D between X and X, it should be 0, and it should be symmetric under the exchange of the density matrices. Now, one of the first distance measure which was used was relative entropy. We cannot strictly call it as a distance measure because it is not symmetric in the variables rho and sigma. So in general, we can call this as a divergence measure. Um, and this measure calculates the entanglement as the distance between the density matrix and the closest separable state, the relative entropy between the density matrix rho and its closest separable state. The While this measure is mathematically valid for any multipartite state, it is not very easy to calculate numerically, because uh, to find the closest separable state, we have to work with a lot of parameters. For example, for a 2-qubit state, uh, we need to parameterize the reference state using 79 parameters. Since we are finding it to the closest separable state, we need to write a parametric form of the reference state, and this means we have to optimize over 79 parameters for 2 qubits. For 3 qubits, this number of parameters scales as 144, and this keeps on increasing exponentially. So beyond 4 qubits, we are not able to find the total amount of entanglement in a system using this measure. So that's one of the basic disadvantage we have with the distance-based measure. Then the next question we have is, we looked at quantum properties like entanglement, steering, and non-locality. The question we have is, are there any other quantum properties apart from entanglement, steering, and non-locality, which are correlations, but they doesn't fall into the same category as these three? The answer is yes. So what is this correlation? This is known as quantum discord, and it was first introduced in 2002 simultaneously in two different works. One was by Olivier and Zurek, and the other was a paper by Henderson and Vedral. But Olivier and Zurek's paper has a more clear explanation of these correlations. So the first question is, like, are all quantum correlations non-local by nature? Olivier and Zurek considers two objects. One is the system and the other is the apparatus. And they say that the system and the apparatus are correlated with each other when the apparatus tries to measure the system. And the total amount of correlation between these two can be measured using the mutual information. Now, this leads us to the question of what is mutual information. In classical information theory, mutual information measures the total correlations in a system. And mutual information for two random variables, x and y, mutual information of x is to y is entropy of x plus entropy of y minus entropy of x comma y. Now, using Bayes relation, the mutual information can also be written in a different form, j of x comma y. And these two definitions of mutual information are equivalent in classical information theory. Um, the next thing we have is quantum mutual information theory. Now we are looking at quantum systems. So we have to look at quantum mutual information. Now, if I find the mutual information between the system and the apparatus for the definition of mutual information based on I, this uh, expression will remain the same. There is actually no change, no difference from the classical expression. But if we look at the expression for J, again we can write it as h of s minus h of s given A. But at this point, we need to define what is s given A. Now, the first work to define this HFS given A was by Cerf and Adami, in which they actually defined HFS given A using this formula, which is like trace of rho SA log 2 of rho S given A. And rho S given A or rho A given B was defined through this expression called as the conditional amplitude operator. Now, while this while this expression looks consistent with the definition of h of x given y, the problem is the conditional amplitude operator, which should have the same characteristics as that of a density matrix. It should have the same characteristics as that of a density matrix, but it doesn't. What happens is the sum of the eigenvalues of this quantity can exceed 1, and this conditional entropy can sometimes become negative. So these two factors actually um, were considered not desirable. So what Olivier and Jurek proposed was, if we have uh, the definition I, we can retain the definition of I as it is, and for J, we have h of s minus h of s given A. Now, when we say S given A, what we mean is we are finding the entropy of the system S when we have knowledge of the system A. So when we have the knowledge of the system A, what it means is we are executing perfect measurements on A, and after executing perfect measurements on A, we are finding the entropy of S comma A. So this is the definition of HS given A. And based on this definition, they constructed the density matrix rho S given A, and consequently the mutual information J of S A. This quantity rho S given A is always positive, and its eigenvalues sum to 1, and the J is always positive. So we got rid of all the undesirable properties we had in Cerf and Adami's work. So once these things have been done, the next important point which they noticed was the I and J are no longer equivalent. The inequivalence comes because I is the mutual information before measurement and J is the mutual information after measurement. So we define a quantity called quantum discord, which is the difference between I minus J, and this quantity is greater than or equal to 0, and this tells us the amount of quantum correlations in the system, because by the mutual information I contains the total quantum correlations in the system, and in J what we did was we did a projective measurement over A, and any projective measurement in a over one of the parties in a bipartite system is going to break all the correlations between the parties, which means we are destroying all the quantum correlations between S and A. So we have the total correlations in which we are destroying the correlations between S and A, and that gives us the total quantum correlations in the system. Now, to verifying this with the quantum state, so the authors considered a Bell state and mm, actually made a Werner state by mixing it with a maximally mixed state, and they measured the discord. The discord falls to zero only when z equal to zero, which is only when it's a maximally mixed state. The system doesn't have any correlations. But it's well known that when we have a Bell state and we mix it with a maximally mixed state, at the point exactly z equal to 1 by 3, the system is no longer entangled. So between the region z equal to 1 by 3 and z equal to 0, the state still has certain quantum correlations, but they are not entanglement. And these quantum correlations are called as local quantum correlations. So now the task is to generalize this for multipartite system. We defined all these quantities for bipartite system. So what are the properties we require to generalize it for a tripartite system? First, let's start with tripartite system. The properties are, it should be zero if and only if the state is a classical state. Number two, it should be a non-negative quantity. And number three, it should reduce to the standard definition of discord for bipartite-like correlated subsystems. Several works attempted to generalize this quantity, but they all failed in that when they defined their measure, there was always one state or a class of states for which these measures failed to find the quantum discord. That is, it does not become zero for all classical states. So we actually decided to pursue this problem, and we looked at it from a different perspective. We looked at quantum discord and thought that, there are two crucial quantities involved in quantum discord. One is the mutual information, and the other is the projective measurement. So we proposed that if we are going to have a generalization of discord, we should have a new quantity called a conditional projective measurement, and then quantum conditional mutual information. With these two things as ingredients, we can propose a tripartite generalization of quantum discord. So when we have a multipartite system, when we need to find quantum discord, we need to carry out more than one projective measurement, because we have to break all the correlations to correlations to count them, which means for a n-partite system, there will be n-1 correlations, and we'll need n-1 projective measurements to measure the quantum correlations. So when we carry out these n-1 measurements, we'll be carrying them out successively, and we would expect each measurement to be conditionally related to the previous measurement. For example, if I have a case where there are two projective measurements, for example, pi AB is a composite projective measurement where I have projective measurement over A and projective measurement over B. So here I carry out the projective measurement A, and my projective measurement B is B where K given J. That is, I have carried out A, and this A has to some extent modified the state, and then I have carried out the projective measurement on the modified state. So based on this, we could define the n projective measurement, n conditional projective measurement. Now, considering this conditional projective measurement, we use the quantum conditional mutual information, where again we have multiple definitions of conditional mutual information. For the bipartite measure, we had three measures. Bipartite we had two measures, I and J, but for the tripartite we have three of them.
Sorry to introduce, sir. Someone has raised a hand. Shall I allow him to ask question?
Yes, please.
Okay, just a minute. Yeah, Arindam, you can speak now. Hello. Arindam, you want to ask something?
Sorry, sir.
Hello.
Hello?
Sorry, sir. So please continue. I accidentally put
Oh,
that.
okay, no
Okay.
problem. Yeah,
No
continue.
problem. No problem. Yeah, yeah. Okay. So in a bipartite mutual information, we have two definitions, I and J. For the conditional mutual information, in the tripartite case, we have three different definitions, I, J, and K, where I is the conditional mutual information without any projective measurement. J is projective measurement on one party, and K is projective measurement on two parties. So along with this conditional mutual information, and quantum, and just the quantum mutual information, this is the tripartite mutual information. We have two of them, I and J. We could define what is called as the conditional bipartite discord. So conditional bipartite discord refers to the let's consider a tripartite system A, B, and C. It refers to the bipartite correlations between A and B once we know the state C. So we define the conditional bipartite discords from AB, AC, and BC. And then we also defined the um, totally tripartite correlations, which means correlations which are unique, which is completely tripartite, which is the difference between the mutual information I and mutual information J. And a sum of these four quantities minimized over the projective measurement gives us the tripartite quantum discord. So here, this quantity actually delta A is to B is to C, which measures the truly tripartite, or what we call as genuinely tripartite quantum correlation. We could write it as dA is to B and dA is to C minus dA is to BC. And this is very similar to what we call as the monogamy relations, which I will come to later in the when we talk about quantum coherence. But using these conditional bipartite discord and the distribution of genuinely tripartite discord, I could actually write down the expression for the total tripartite discord. Now, we actually checked it out for a few generic states. Now, to consider the entire class of generic states, actually, we could consider for a very different kinds of states, but usually tripartite states are divided into two unique classes, namely the GHZ class and the W class. The GHZ class consists of states of the form 000 plus 111 by root 2, and the W is the 001 plus 010 plus 100 state. Actually, there's a typographic error here. We considered these two tripartite states and constructed a Werner type mixed state using these tripartite states, and found the tripartite discord as found the variation of tripartite discord with the mixing parameter. We could see that the tripartite discord has always been positive, and it is 0 only when mu is equal to 0. That's only when the state is classical, and it satisfies all the properties we expected out of the bipartite bipartite discord. So the same thing was observed for the W state as well, where the discord was found to be 0 only when mu is equal to 0. So this was a very successful definition for the for the multipartite discord. And later we verified this using experiments, and we published our results in the Proceedings of the National Academy of Sciences. In this experiment, we considered NMR qubits and we constructed 3-qubit states, namely the GSE state and the W state. And we constructed actually Werner type GSE and Werner type W state. And we measured the variation of discord with this. And the results we got in the experiment actually matched exactly with the theoretical results we had previously. The theoretical paper was published in 2021, I think, 2020. And this experimental paper was published last year. And it matched exactly. And here we can see that the GSE state, generally a GSE state doesn't have entanglement beyond the point mu is equal to 0.2, but we can see that it still has a finite amount of quantum correlations here. And for a W state, doesn't have entanglement beyond 1.6. And we can see that still there is a finite amount of quantum correlations in this region. So this is about this resource quantum discord. The next thing I want to talk is about quantum coherence. So beyond quantum discord, are there any other properties which is inclusive of quantum discord and which can also be used as a resource? The answer is we have a property called coherence, which actually encloses discord and all the other correlations we know so far. So the first question is, like, how do we measure quantum coherence? Now, the first work on measuring quantum coherence was proposed by Baumgartz, Kramer, and Plinio in 2014. Here they introduced 3 core concepts, namely incoherent states, the maximally coherent states, and the incoherent operations. The incoherent states are the states which does not have any quantum coherence. These are very important because in any resource theory, if we want to measure a resource, one of the important things which we need to know is the set of 0 resources, so that we can find how far the state we have is away from the set of 0 resources. So we need to define incoherent states, and an incoherent state is defined as a state in which the density matrix has elements only along the diagonal. Then maximally coherent state is the state in which the density matrix has elements, or all the elements in the density matrix are equal. Finally, we have the incoherent operations, which means operations which act on a given state and does not create any new coherence, which means if these operations, for example, the Krauss operations, act on an incoherent state, the state still remains in coherence. These are called incoherent operations. Now, as a resource, coherence should have the following properties. It is equal to 0, or it should be equal to 0 for all incoherent states. It is equal to 0 if and only if the state delta is incoherent. Then it should satisfy monotonicity under ICP-TP maps, which is incoherent completely positive trace preserving map, and under selective measurements, and it should verify convexity. These are the defining properties of quantum coherence. In fact, these are in general considered as the defining properties of any resource theory. So, monotonicity means any measure of coherence should vanish for incoherent states, and it cannot increase under incoherent operations. And convexity means the resource should be non-increasing under classical mixing of quantum states. So based on these properties, measures of coherence were proposed. In the paper by which in the first paper by Baumgartz, they proposed two different measures. They said that if C is a coherence measure for a density matrix, we can propose distance-based measures where we find the distance from the arbitrary state or the given state to the closest reference state, which is the reference state. And this reference state, we can consider it to be the set of incoherent states and find the closest state. The minimization is to find the closest incoherent state. So now what are the distance measures which can be used in this scenario? The distance measures we can use here are measures which are contracting under CPTP map. Contracting means under any CPTP map, the distance measure should not increase. That is, it should be greater, it should be less than or equal to the distance without the map. Okay. Now, based on these two properties, they propose two measures. One is the relative entropy of coherence and the other is the L1 norm of coherence. For both these measures, they gave a mathematical proof which said that the closest reference state or the closest incoherent state to this state rho is the diagonal state. So there is no need for minimization in this process. Okay. Now these two measures were proposed. In our work, we actually considered a different measure, which is called as the Jensen-Shannon divergence measure of quantum coherence. And the motivation for using this measure is as follows. The relative entropy is not strictly a distance. Actually, when I was explaining entanglement, I said that relative entropy is not symmetric in the arguments of rho and sigma. We can see this from the expression here. So it is not strictly a distance. And the second problem we have is, since it is not symmetric in the arguments of rho and sigma, it also has a support problem, which means when we have this expression, the number of non-trivial eigenvalues of sigma should be greater than or equal to the number of non-trivial eigenvalues of rho. If we have this to be less than the number of non-trivial eigenvalues of rho, then we are going to have unwanted infinities. To overcome this, there is a measure called the Jensen-Shannon divergence, where we consider the relative entropy between rho and rho plus sigma by 2. And we actually do that rho plus sigma by 2 and sigma to rho plus sigma by 2. And this measure is called as the Jensen-Shannon divergence. And Jensen-Shannon divergence lies between 0 and 1. As such, Jensen-Shannon divergence is a distance, but it's not a metric. But if you take the square root of Jensen-Shannon divergence, it is both a distance and a metric. And the quantum version is a distance and a metric for both pure and mixed states. And this has been proved mathematically. Now, based on we can, this relative entropy expressions, we can actually simplify to just entropies of the density matrices. It's just mathematically we can derive this relation. And based on this, we gave the measure of quantum coherence. But before that, we had a crucial question to ask, like when we are looking at coherence, when we have multi-partite system, like let's say I have 4 particles, coherence can arise due to two different natures. One is the superposition between the particles, which is like here I have 4 particles and I denote each one by a black colored circle, and I can have superposition between each one of them and I can get a coherence. And then I can get a coherence because of the superposition between the levels within a single qubit. Now, this superposition due to the levels within a single qubit, I call this as the local coherence, and the superposition between the different qubits, I call them as the intrinsic coherence. So to find the intrinsic coherence, I find the distance from the density matrix rho to the closest separable state. And then to find the local coherence, I find it from the separable state to the incoherent state. So we could show that these three measures, like the total coherence, which is the distance from rho to rho d, that is the closest incoherent state, local coherence and the intrinsic coherence together, they form the three sides of a triangle and satisfy this inequality, where the total coherence is less than or equal to the sum of the local and the intrinsic coherence. To actually check this out, we worked it out for a small toy model. We considered a transverse Ising model, just 2-qubit system, and we studied the quantum coherence in this model, and as a function of the interaction parameter j by lambda. When j by lambda is equal to 0, the state was the maximally entangled Bell state, and so it had the intrinsic coherence was maximal and the local coherence was 0. And as we increased j by lambda, the local coherence started increasing and the intrinsic coherence started decreasing. And beyond a point, the intrinsic coherence reached 0. The local coherence became maximum, somewhere around j by lambda equal to 2. Let me say it's large j by lambda. What happens at this point is the ground state is the product state 0 minus 1 and 0 minus 1. That is minus minus in the x basis. Now, this is quantum coherence in the for 2-qubit system. We next verified the quantum coherence for 3-qubit system. Just like Discord, we verified it for the tripartite states, GHZ and W states. And we verified it by constructing the Werner type states for GHZ and W and finding the coherence as a variation of the parameters, mixing parameter. The next quantity we defined was the distribution of coherence. Now, in entanglement, there is a expression called the monogamy of entanglement, which means entanglement between entanglement. Let's consider a tripartite system, which has 3 parties A, B, and C. Here, the entanglement between the party A and the block BC is greater than or equal to the entanglement between AB and the entanglement between AC. In this stage, AB and AC, the other party is usually traced out. Okay, this inequality is called as the monogamy of entanglement, and any quantum state which satisfies this inequality is called as monogamous state, and states which do not satisfy this relation is called as polygamous. This relation was first introduced by Kaufman, Kundu, and Utters, and later on it was generalized for multipartite systems, where even in the multipartite system, we consider the entanglement between only the first party and the remaining block and compare it with the bipartite entanglements. So this in general called as the monogamy of entanglement for multipartite systems. But we can always come up with much stronger conditions where we look at this blockwise thing with bipartite, then the tripartite and higher order things. And such a relation is called the stronger monogamy of entanglement. But in our work, we focused only on the monogamy of monogamy based on the regular definitions by Kaufman and Osborne. So we defined a monogamy of coherence relation for multipartite system, and we actually found this value M, and we could see that for a GHZ state, M was always less than or equal to 0, and for a W state, M was greater than or equal to 0. What this means is, when we have a GHZ state, the coherence is distributed in a genuinely tripartite manner such that if I trace out one of the qubit, I lose all the coherence in the system. I can consider this coherence as some kind of a, circular path on which all the three qubits are embedded. And by removing this qubit, I am breaking up this circular path and I lose the entire coherence in the system. Now, for the W state, the coherence is distributed in a bipartite way. That is, we have three qubits, but at any given point, the coherence is always distributed in a bipartite way where AB, BC, and AC are coherently connected. But if I trace out, let's say, one of the qubit, I would still have the coherence between the other two qubits. So then after introducing this monogamy relation, we checked out the coherence and monogamy expressions for a spin model. We looked at the Heisenberg XXZ spin chain. So the Hamiltonian of an Heisenberg XXZ spin chain is given here. Here J is the spin-spin interaction parameter and delta is the anisotropy parameter. When delta is less than -1, the coherence C is 0 because the state is completely ferromagnetic and so the state is very unique. Now, when delta is very much large than 1, the state is a bipartite Neal state, which has the superposition 0101 and 1010, which is very similar to a GHZ state, and it has the same amount of coherence as a GHZ state. The two-site coherence C1:n, that is, when we trace out all the other things and find 1:2 or 1:3 and so on, they actually decrease with distance. But as we can see that 1:2 is higher and 1:6 is actually very low. So here in this model, we considered a spin chain with just 12 spins. And then we also looked at the monogamy of the spin chain. And we found that the monogamy, initially the state is actually, there is no monogamy or polygamy at this point because there's no coherence. And then here it is monogamous, and then it becomes polygamous for very large delta. So based on the value of the delta, the distribution of coherence in the spin chain actually changes from relatively local to genuinely multipartite. So we actually verified all these distribution relations and of quantum coherence in our work, which was published in NPJ Quantum Information. And then we studied this with respect to a spin model, XY model, with the DM interaction, Zyloshinsky-Moria interaction, which is nothing but a spin-orbit interaction. The Hamiltonian of the XY model is actually given here. Here J is the spin-spin interaction and D stands for the DM interaction, and gamma is the anisotropy parameter. For gamma equal to 0, we will have the X model, and gamma equal to 1, we have the transverse Ising model, and for the remaining values of gamma, we have the XY model. And for J less than 0, we have ferromagnetic, and J greater than or less 1, we have a antiferromagnetic thing. And there's actually a phase transition at J equal to 1. So from the measurement of quantum coherence, we could actually find the signatures of phase transition. So here we considered an infinite spin chain, and we considered the bipartite density matrix between two spins like I and I plus 1, and we could find the signature of phase transition, and we can find the same signatures for two spins which are located a little bit far away, like I is 1 and I is equal to 5 kind of a distance. So we could see that we can always find the phase transition using quantum coherence. Now, these results are very similar to the results one might obtain with entanglement, but the significance of these results lie in the fact that if we want to study quantum phase transitions using entanglement, one of the primary problems you would run into is measuring entanglement for more than 2 or 3 particles. So when we have multipartite states, it is hard to quantify entanglement and find the phase transitions. But if we can find the coherence, because coherence is easy to find since there is no optimization involved, we can actually find the phase transitions in such systems much easily. So finally, I would like to talk about our recent work in which we looked at the influence of non-inertial motion on quantum resources. So most of the times we study quantum states which are in inertial frames. So there is also an interest among information theory researchers to study quantum systems in non-inertial frames. By that, what we mean is when we have, let's say we have 2 qubits, one qubit is with Alice and the other qubit is with Bob. Bob actually, instead of staying inertial, he accelerates and starts moving away from Alice. Now, how do the properties of the bipartite system change when Bob actually travels with an acceleration? Now, usually quantum states in the inertial frame are described using Minkowski coordinates in the Minkowski space-time. But for a non-inertial system, we have to describe them using Rindler coordinates in Minkowski space-time. So what happens is the quantum state actually kind of like is split into 2 parts between Rindler regions 1 and 2, and these two parts are causally disconnected. So what is happening is when we have a relativistically or non-inertially moving state, actually the environment works as kind of an external bath, and it kind of degrades the quality of the quantum state. So when this happens, the vacuum state actually can be, we can show that the vacuum state actually changes to this infinite mode state, and the first excited state changes to this new infinite mode state. And based on this, actually, we gave a theorem which says that if we have a n-partite system in which m subsystems, that is m is less than n, and m subsystems are under non-inertial motion, the effect, which is the Unruh effect, which causes the external environment to behave as kind of the vacuum to behave as a virtual bath, this Unruh effect can be actually represented by a CPTP map and we give a complete description of the map. So how this helps us is we can quantify the changes in the quantum state due to non-inertial motion as a kind of a noise. And any quantum resource theory actually rests on 3 pillars: the free states, the free operations, and the resource quantifiers. Now, free states are the states with 0 resource. Free operations are the states which do not create any resource in the 0 resource states. And resource quantifiers, these are measures which help us to quantify the resource. These 3 ingredients are needed to describe a resource theory. So what we showed in our work is, we showed that in the free state, the non-inertial map redistributes resources across field modes. And so part of the resource might be lost, but free states remain free. And also, the geometry of the free state is preserved. That is, if a particular resource has a set of free states which is convex in an inertial frame, then this convex structure is maintained in the non-inertial frame as well. Then we checked out the resource quantifiers. The resource quantifiers can be broadly classified into three different types, namely convex monotones. One of the example is we can say that concurrence is a convex monotone of entanglement. Then robustness based measure. Robustness of entanglement is a robustness based measure, and distance based quantifier. An example is the relative entropy of entanglement. And when we look at these three different sets of quantifiers, if any one of them can be used in an inertial scenario, let's say I can use concurrence to measure entanglement between a two qubit state, then I accelerate one of the state, then I'll be able to use concurrence to still measure the entanglement in the non-inertial states as well. Okay, so we proved these statements mathematically in our recent work, and yes, so that's the end of my talk. So what I talked about today is quantum resource theory, which is a mathematical work in quantum information theory. And in particular, I talked about the different resources I worked with: quantum discord and quantum coherence. So usually when we look at the theory of quantum resources, people will say that apart from the property that it should be greater than or equal to zero, there are two core properties, monotonicity and convexity. Only if it satisfies all three properties, generally it is considered as a resource. But quantum discord doesn't satisfy convexity. But though it doesn't satisfy convexity, it is one of the quantum correlations and can be considered as a resource in a more technical sense. And then I talked about what happens to quantum resources under non-inertial motion, particularly when the states, particularly to the properties like free states, free operations, and the resource quantifiers. Okay, and thank you very much for the opportunity. And if you have any questions, I'll be happy to take them now.
Yeah, thank you, sir, so much. It was a very interesting session that we had, and I know it's so much pleasure to work with you. And I can see lots of participants are there who wants to ask questions. So I'm just allowing them so that
Sure.
they can put their questions. Just a minute.
Yes.
So first of all, I am allowing Shailpreet. Let me introduce Shailpreet to you. Shailpreet is actually a student from ITR Bhubaneswar. He
Mhm.
is learning this quantum physics, quantum information, entanglement, and coherence. So he wants to ask a question. Shail, go on.
Yes, sir. Hello, sir. Thank you for the talk.
Hello, Shail. Yeah,
Sir,
Shail, can you be a bit loud actually?
okay, sir. Sir,
Yeah,
thank you for the talk. I'm sorry to pull you away from what you've been teaching us. Uh, Actually, I'm just I'm just starting on the topic of quantum computing, so I don't know much. I would like to know because you showed us many different kinds of maps and mathematics. So I would like to know what I need to know to pursue the topic that you are working on.
Oh, you mean quantum resource theories, like a kind of thing?
Yes, sir.
Okay. So if you want to actually generally look at quantum resource theories, I would actually direct you to read. There's a very nice review articles in reviews of modern physics. Um, One is the quantum resource theory of coherence by Alexander Streltsov. And there is another article by Eric Chitambar on resource theories, Eric Chitambar and Girard Gaur. Actually, if you get there, you will see a more mathematical. I have actually tried to keep away from the mathematical descriptions, but a more mathematical description of the set of quantities, like what I'm talking about, the free states, free operations, and all those things. Probably that would be a great place for you to start with. Yeah.
Okay, sir.
Okay, Shail, any more question?
No, sir. Could you please repeat like the first name, quantum resource theory of coherence by
Oh,
Alexander?
yeah, sure. Alexander Streltsov. Streltsov as in
Okay, sir.
Strelsov.
Okay, thank you, sir.
Yeah.
Okay, thank you, Shail. Sir, we have Manidulda with us, so he wants to say something.
Yeah. Hello, Mani.
Manida, you unmute yourself and speak. You can.
Hi,
Hello.
Chandra.
Hi, Mani. How are you?
I'm fine. I'm fine. Very nice talk. So thank you very much for this very interesting and insightful talk. And it is always a pleasure to listen to Dr. Chandrasekhar Radhakrishnan, especially on a subject as deep and evolving as quantum resource theory. And having known and interacted with him over a long period of time, actually Chandra and me, we are working since together on several problems on quantum resource theory since 2016, I think, I guess, when I was in Taiwan and he was in Shanghai. So having known and interacted with him over a long period, and here in Chennai also we used to meet when he was in IIT Madras. So having known and interacted with him over a long period of time, I can truly appreciate the clarity and originality he brings to the complex problems and ideas. And today's talk once again reflects his ability to connect abstract resource theoretical concepts with broader physical intuition. What I find particularly compelling is how the framework of quantum resource theories continues to unify diverse concepts like entanglement, discord, coherence, etc. And again, this coherence has this local and global coherence, intrinsic coherence, and beyond. So all these things under a common language of quantum resource. So talks like this is not only deepen our understanding, but also inspire us or also inspire new directions for future research or exploration. So I would like to congratulate him on this excellent presentation and thank him for sharing his insights with us. I look forward to further discussions with Chandra and developments emerging from this line of work. Thank you, Chandra, for this nice talk.
Sure, Mani. Thank you very much, Mani. I look forward to working with you.
Okay.
Sure.
Sir, we have now with us Dr. Biplav Ghosh. He's with him. We did our first work in which was
Yeah.
published in IJQI. So Biplav, you want to say something? So or you can ask. Unmute yourself and ask. It would be nice if you can switch on your video. Hello, Biplav. Hello. Probably he is having some trouble. And sir, you can before he asks question, you can see one question has been put forward by one of the participants, Rupayan Bhattacharya. He has written the question in the chat box.
Oh, yeah, sure. Assets required to implement a quantum algorithm or achieve advantage. The list of resources do not include space, time, or energy. Okay.
First of all, since we are recording this, I'm reading the question so that everybody can listen to it. Okay. So he's asking that I'm sending a question via chat as I'm in a noisy environment. The talk starts with a definition of quantum resources as assets required to implement a quantum algorithm or achieve advantage. However, The list of resources do not include space, time, or energy which are required for executing any algorithm, quantum or classical. Additionally, the relationship between these resources, such as entanglement and the performance of quantum algorithms, is not well understood. It is not well understood how these resources affect quantum algorithms. Then why are these resources important? Are there any real world applications of quantifications of such resources? Are the quantitative values of these resources useful in gaining insights into their applicability in quantum algorithms, communication protocols, or sensing? The question put forward by Rupayan Bhattacharya, sir.
Okay. Okay. The first point is the point about space, time, and energy being resources. I was actually pitching it from the classical computing angle. So if we look at classical computing, and if we look at it from a Turing machine point of view, space and time are the resources. And now we have a new resource because we need to have a sufficient amount of energy to run the machine to do some computing. So now, beyond this, we need to gain computational advantage, and we are looking at quantum systems, which has certain properties which are not present in classical systems, which can gainfully used for us, right? So one of the things I said was entanglement. Now, entanglement is as such as its applications in, let's say, if we go to quantum communication, the E91 protocol, we are definitely using it as a resource in a communication protocol. Now, superposition is definitely a resource when we go to several quantum algorithms, actually, because the starting point of any algorithm is first we make a superposition of quantum states. Actually, when you do computation, there are three important things we need. One is create a superposition. Then the second point is we need to correlate the states. One of the best correlations we know is entanglement. And the third is we need to use the principle of interference to filter out the wrong answers and get the right answers in. These are the three core principles on which quantum computing works. And superposition is a resource. I did not talk about it today because I have not worked on it. Entire coherence but technically speaking, what we look at as coherence in our work is essentially manifestation of the quantum superposition. Okay, so these are all resources which help us to gain advantage and actually help us to do quantum algorithms. But there is a better resource now, which about which we have recently written a paper. Unfortunately, I could not talk about it today because the paper we submitted as which is under review with Nature, we are under strict what do you call us, like strict limitation as to not to talk about it until the review gets over. But there is a quantity called as quantum magic. And what magic is, it actually, we all know about this Nil-Leflam theorem, which says that if we have a set of, if we have a quantum circuit which can be composed of only Clifford set of gates, then we can efficiently simulate it on a classical computer. So if we have a problem which uses only Clifford set of gates for an algorithm, then that problem can be simulated on a classical computer. If not, then it can be simulated only on a quantum computer. And any state which has this extra resource, non-Clifford nature, is referred to as quantum magic. It's a very new topic. And actually, it was an open problem for a long time about how to quantify magic for mixed states until we solved it last year when this work was published in PRL. So magic is kind of like a resource which is very directly connected with the algorithm and gainful exploitation of as a resource for a purpose, for a definite purpose, as the question asks. Yeah. Thank you.
Okay, sir. Now we have, it's a very interesting thing. Whenever we actually talk to you, we gain new insights in quantum information. And now we have with us Dr. Anushri Pandey. She is one of our collaborators from the IGQI paper. So she wants to ask a question. Anushri,
Sure.
go ahead. Anushri, unmute yourself and ask. Hello. Anushri, you raised your hand. You can ask question. I think she is having some trouble.
Anyway, I think Professor Surajit Sen has also raised his hand.
Yes.
Professor Sen has also raised his
Yeah,
hand.
Yeah. Sir,
Yeah.
please.
Can we talk with him?
Thank you, Professor Chandra. This is a wonderful talk. So I have one very naive question from context of quantum optics. That recently we have seen that there is a very relationship between the Lie algebra and various quantum mechanical 2-level, 3-level, or and n-level systems with Lie group, right? Various quantum mechanical systems. So whatever you were telling, that is there any relationship between the real algebra or the group sorts of thing in your description?
Oh, yeah, sure.
Professor. Because ultimately you have to connect it with various level systems, right? Quantum optical systems.
Yes.
Once you want to translate it into some reality. So that's aspect.
Okay, Professor Sen. It's a very interesting question. I don't have a direct, complete answer to this question, but from the framework of Lie algebra, I know of few things which are being explored as a resource. So, after entanglement and discord, actually the first time the word quantum resource or resource theory was actually used by a Canadian professor by name Gilad Gaur. Right now he's in Israel, I think, Israel, in some university in Israel. So he proposed a resource called asymmetry, which means any quantum state which has some kind of a symmetry which can be exploited is symmetric, and if it doesn't have that symmetry, it is asymmetric. And these symmetries are characterized by the Lie algebra. And so you can have this zero set measure states as the states of what do you call as okay. Zero states are the states which do not have the Lie algebraic symmetry, and you have something called, I forget the name. There's a technical word for getting rid of the symmetries and so on. Twirling operations to find these resources and so on. And this idea of frameness has been explored in several directions, not just for rotation, but in several other contexts. But one of the other thing from a group theory point of view is the entire idea of quantum magic I was talking about comes from the fact that this Clifford set of gates form a group. And anything which is non-Clifford is being out of the group symmetry. So in some way, we are actually connecting a group symmetric thing and trying to look at it from a quantum resource theory perspective. These are the vague things I know, but technically, I do not have a direct answer to how these can be actually done or it in the future, actually. But it's a very interesting question that you asked. Because symmetries are going to help us to exploit the quantum states in a better way than what we can do now.
Okay, thank you.
Okay, sir. So, Anushri, you can ask question now. Probably you had some network issue.
Yeah. Good evening, sir. Thank you
Good
for
evening.
such a nice talk. We had a collaboration together as well. So myself, Anushri Pandey. So the thing is that you have discussed regarding the quantum resource theory. So one simple question, that is there a known hierarchy among the resources you will discuss? Like we can say that entanglement is more powerful resource than quantum coherence, or do they represent fundamentally different types of non-classicality that are useful for distinct variable tasks?
Okay, so there is definitely a hierarchy. Actually, a resource now is a broad spectrum. Like right now, I know there are close to 20 different resources now. Of these 20 different resources, some of them fit into a hierarchy. For example, when I was showing the slides, the slide I showed non-locality, followed by steering, followed by discord, followed by coherence. That is the hierarchy we had so far. Now I have a new paper in which I describe one level above it, which is purity. Okay. So, so this set as a hierarchy, but there are other resources, like for example, this magic I was talking about, that doesn't fit in this hierarchy, because there are entangled states which do not have magic, and there are separable states which have magic. So it doesn't fit in this hierarchy. And then contextuality, there is something called imaginarity, a non-Markovianity. All these things do not fit into this hierarchy. So we can actually split them into two parts: the ones which fit into the hierarchy and the other ones which do not fit into the hierarchy. But from my perspective, like a better hierarchy is a hierarchy in which we look at the set of zero states, which is the set of free states in the resource theory. Based on that, we have a very nice hierarchy. The first one is we have an affine set. That is, the set of zero states form an affine, can only form an affine combination. And then we have a convex set, and then we have a non-convex set. So there's a hierarchy between this, and every resource theory can be captured into any one of these three sets, actually.
Okay.
That's another way of looking at it. Yeah.
Yes. Okay, sir. Thank you, sir.
But you can find a description of this on the archive paper I have listed on the thing, the relativistic quantum resource theory paper, this year's paper. I have listed, I have given a brief description of these three hierarchies: affine, convex, and non-convex resources.
Okay, sir. I'll get into it. Okay.
Yeah,
Thank you.
Thank you.
I have one question, sir. Since you have mentioned a monogamy relation in 3-qubit system, so in qubit system, do we have any sort of such relation in monogamy type?
Yeah. For example, the monogamy relations do not depend on the levels of the system, Shoaib. They depend on the part type. So, for example, there's a distinction. Being bipartite and being a qubit are two different things, right? So monogamy relations are defined for bipartite, tripartite, multipartite, and so on. And these partites or each parties can be 2-level, 3-level, n-level, anything. The same inequalities will hold, can be proposed. These are not inequalities in the sense like which are satisfied. These are inequalities we propose, and based on that, we classify the states into two types or different types. Okay, and this different types of states have different distributions of quantum resources.
So anybody else has any question you can ask? Any other question from participants? No. If not, then I shall first of all ask Professor Surojit Sen sir to give vote of thanks to our speaker. Sir, please go ahead.
Yeah. Thank you, Professor Chandrasekhar. So for your illuminating talk and thought-provoking particularly, and your valuable this participation, deep expertise, as well as this engaging presentation has greatly enriched us. And very special thanks, particularly you have joined from different time zone. Wow. So once again, I thank you very much. Then we think we shall get your cooperation for the growth of this newly funded center. Thank you, sir.
Thank you very much, Professor Sen. It was my pleasure to give this talk. And I'd also like to thank Souvik for organizing everything so seamlessly.
Thank you, sir.
Thank
And
you.
before I request Atanu to go for today's closing remarks and vote of thanks, I shall first of all ask all the MEM participants to please switch on for your videos for a second so that I can quickly take a screenshot. All of you, please just Anurulda, yeah. Anushri, Shailpreet, others, please. Yeah, okay. Togoto is there. Okay, thank you. Now, Otunu, you can give a vote of thanks and closing remarks to our
More
session.
people are there.
Yeah, more people are there, but all I can't. Yeah. Okay. Others are also. I'm unable to manage actually. I cannot see all of them in the screen.
Okay.
Can you Otunu? Can you see all of them?
Yeah, thank you, Sovik.
Then you can take a screenshot. In my screen, all of them are not visible.
Yeah, I can see 15 actually.
Yeah. Then you can take a screenshot. Okay, take a screenshot.
Oh, seven people are.
Yeah, I just took. Just missing actually.
Yeah.
Rupayan, if you are there, then start her. Great.
Once you are done, you tell me.
Yeah, I'm done. Okay, Tushar sir is here. Let me take another one.
And Professor Bimalandu Dev is also there.
Yeah, Rupayan and
Souvik?
Yeah, I think. Yeah. Bimalandu sir is also there. Yeah.
Okay.
All is on.
Okay, done.
Okay, thank you. Preserve it. And Atanu, please go for your closing remarks and vote of thanks.
Sure. Yeah, so finally, on behalf of Cassie Lab, I'd like to make some closing remarks on our month-long seminar series. We send our deepest gratitude to the eminent physicist, Professor Haridas, Professor Panigrahi, Professor Lakshmi Bala, and Professor Chandrasekhar for their stimulating lectures over the past several weekends. The profound insights into quantum physics made these sessions truly memorable, and the materials they have shared will serve as a valuable resource for our audience. We extend our special thanks to the faculty, independent researchers, and students whose presence and enthusiasm were crucial to the success of this series. We look forward to your continued support as we work toward establishing a unified framework that brings together independent researchers and institutional scholars under a single umbrella, a core mission of Cassie Lab. Finally, I acknowledge our dedicated organizing team for their seamless coordination over the past few weeks. We conclude the phase 1 of our Saturday online seminar series 2026 today and look forward to returning soon with new collaborations in phase 2. Thank you all.
Thank you so much, and thank you for participating. Thank you, sir. I think I know you are in China. It is what is the time now?
It's going to be 11 in another 5 minutes.
Okay, sir. You have your dinner and.
Yeah. I had my dinner.
Okay.
Thank you. And Souvik, Professor Radhakrishnan is joined actually.
Oh, okay. Sir, you want to say something?
Thank you very much, sir.
Balakrishnan, sir, you want to say something? You can.
Yeah.
Please. You unmute yourself.
Yes. It was a wonderful talk. Extremely wonderful talk. Thank you very much.
Thank you very much, Professor Balakrishnan. Thank you.
Really lovely.
Thank you.
Thank you.
Thank you, sir. Okay. So we can leave now. Thank you so much. Thank you for
Thank
joining.
you.
Yeah.
Thank you, sir. Thank you. Thank you, Joey. Thank you.
Thank you.
Good night. Good night. Bye.